Okay, in last lecture we have discussed something about LPP, linear programming problems. In last class I have discussed the basic about LPP and I have taken an example related to the graphical method. Basically we have discussed about the graphical method, and in last video example we have seen the solution of the problem means the optimal solution is the unique solution. In today's class I will discuss the different aspect of the LPP. The different aspect of LPP means the problem maybe have the unique optimal solution, and there is a possibility the problem has multiple optimal solution, the problem has no solution, and the problem has unbound solution. In the last video example I have taken an example of a problem that belongs to the unique optimal solution. Unique optimal solution means there is only one possible combination of decision variable at which the value is optimal, right? So this example we have discussed already, and in today's class I will discuss these three examples how a LPP can be solved is related to the multiple optimal solution, no solution, and unbound solution. By considering, I will demonstrate all these aspectation of the LPP by taking a considerable example, right? So multiple optimal solution, before starting in detailing, I am just giving the brief about how a problem can be a multiple optimal solution. Multiple optimal solution means if there are different combination of decision variables to obtain a single optimum value, means we have more than one corner point at which the value is optimal. So that type of problem is called multiple optimal solution, right? And by seeing the mathematical description of any problem, we can easily identify before starting the problem is related to the multiple optimal solution. And I will show you in the slide how we can recognize a problem belongs to the multiple optimal solution before starting the problem. No solution means we are unable to find any feasible solution. Means the description of the problem in such a way, or you can say the mathematical form of the problem in such a way, we are unable to identify a feasible region. If we are unable to find out a feasible region means a common region in which the solution lies, right? So then we can say that problem has no solution. Unbound solution means unboundness sometimes happen due to the if any description form is not formulating properly into the mathematical form, because in industry the problem is always in the description form. If we want to convert that description into the mathematical form, it requires four things: decision variables, objective functions, constraint, or you can say the restriction, and non-negativity restrictions. If we are unable to convert properly, then sometimes the unboundness occur, right? So I will discuss all these aspects step by step, so that, and I will also demonstrate by considering the example, so that we can get the better understanding of this LPP different aspect. So multiple optimal solution, in multiple optimal solution, you can see a LPP may have same optimal value of the objective function at more than one corner point. Means we have the different combination of decision variable to get the optimum value, right? How we can identify before starting the problem? We can identify if we check the slope of the objective function. If the slope of the objective function is same as the slope of any of the constraint. If the slope of the objective function is same as the slope of any of the constraint, then we can say that constraint is known as the binding constraint. If that binding constraint forms the boundary of a feasible region, or you can say that line is parallel to the objective function line, then that problem has a multiple optimal solution. Then we can say that problem has a multiple optimal solution before starting, right? So I will demonstrate, or I can say, in other words, I can say the second point I can consider, if I put the optimal point in that constraint, that is the binding constraint, then always left hand side is equal to the right hand side, or that constraint is also known as the active constraint. that binding constraint is also known as the active constraint if the constraint shoots from a boundary of the feasible region in the direction of the optimal movement of the objective function line, is that the constraint should be the active constraint. That binding constraint is called as the active constraint if we are moving objective function direction in the movement of optimal direction, then the constraint is also known as the active constraint. So we can consider this by considering an example. We are taking an example of machining, and this problem indicates the multiple optimal solution. This is the description of the problem. A firm uses lathes, milling and grinding machines to produce the machining parts. Following table represents machining time required for each part, the machining time available on different machines and the profit on the each machine's parts. So this table is given. With the help of this table, actually this is the description is given, and we have to first convert into the mathematical form. Any description can be converted into the mathematical form. Four things are required. One is the decision variable. How we decide the decision variable? On the basis of the requirement of the question. Such in this question, the requirement of the question, how many parts 1 and 2 be manufactured per week. So from here we can decide the decision variables. Suppose the part 1 produce x1 and the part 2 produce x2 per week. So these are the decision variables. Second thing is the objective, and how we can get the objective? Again, from the requirement of the question, the problem of maximize the profit. How many part 1 and 2 produce per week so that we can maximize the profit. So the objective function of maximization of the profit. So we can write here the objective function just like it is the maximization type, and z max is equal to, and if we are producing part 1 we are getting the 40s unit profit. If we are producing x1 is the quantity of the part 1 plus 100 x2. So that becomes the objective function. First we decided the decision variable, second we decide the objective function. Now the third requirement is the constraint. Constraint means the restriction to produce such much profit. What are the restriction? What are the restriction in this organization to produce this much of profit? So restriction is given the lathe machine, milling machine and grinding machine. There are 3 different machines, and the machining time is given for each. So lathe machine required 12 x1 to produce part 1 plus 6 x2 for the part 2, and the maximum available time. The question indicating the maximum. Whenever the maximum is represented, always consider a constraint of less than or equal to. If there is a minimum, if the minimum terms is given, then always consider a constraint of greater than and equal to type. If there is exact, then you can consider a constraint of equality type. So by reading question and availability on the basis, we can decide the constraint, either it is less than or greater than type. So here the maximum time availability per week is given for each lathe, milling and grinding. So the maximum time is given, so that's why the constraint is less than and equal to type. Same way for milling machine, we can produce 4x1 plus 10x2 less than and equal to 2000. Same way we can produce for the grinding machine, 2x1 plus 3x2 is less than equal to 900. So this way. And another very important equation, fourth one, that is non-negativity restriction. Non-negativity restriction. Non-negativity restriction. That is, all decision variable must be greater than or equal to 0. So these are the 4 equations. Equation number 1. These are the 4 things are required to convert any description into the mathematical form, just like decision variable, objective function, constraint and the non-negativity restriction, right? Once we convert it into the mathematical form, then we can plot on the graph, right? Before plotting, we can easily identify, suppose this is the description is converted into the mathematical form. In the last slide I have converted, it is written here. Now before starting the solution of the problem, this problem can be solved either by graphical method, algebraic method or simple X method. Today I am going to discuss the graphical method, so that's why I will solve this problem with the help of graphical method. So before starting the solution, before draw these lines on the graph, I can easily identify this problem belongs to the multiple optimal solution or not. How can I decide? How can I judge? So I just check the slope of this objective function. What is the slope of this objective function? If you are plotting against on abscissa you are representing x1, on ordinate you are representing x2. So if you are finding the slope of this curve, the slope of this curve is dx2 over dx1. So dx2 over dx1 for this line, if you are differentiating it, so that will be 40 dx1 plus 100 dx2 is equal to 0. So what is this? Dx2 over dx1 is here in this case, that is minus 40 upon 100, and minus 40 upon 100 is what? Minus 2 upon 5. So that is the slope of the objective function. Now I have to check any of the constraint has the same slope. So I am going to check the slope of this constraint is, again if I am calculating, so dx2 over dx1 for this line is, you can write minus, just like so dx2 that is minus 2, not the same one. If you are calculating the slope of this line is dx2 over dx1, that is again same, you will get the value same, minus 2.5. The slope of this constraint is same as the slope of this objective function line. So we can say this constraint is a binding constraint. This constraint is a binding constraint. If any problem, if any mathematical formulation has a binding constraint, then there is always a possibility the problem has multiple optimal solution. Multiple optimal solution means the problem has more than one corner point for a single optimal value, means the different combination of decision variable to get the optimal value, right? So there is a possibility this problem has optimal solution, multiple optimal solution, or I can say alternate optimal solution. So I can solve with the help of a graphical method. In last video I have discussed how a problem can be drawn a graph, right? So there is a possibility we can consider a proper scale, or we can draw on the, just like if graph is available to us, so we can consider any scale, or we can draw on the plain paper by taking some particular range on that paper, just like 1 centimeter is equal to 1 unit, just like this we can plot. So how we can plot? We have to write the coordinate of all these equations. So easily we can write the coordinate. Once we write the coordinate of all the equations, we can plot on the graph. Easily we can write the coordinate just like this in this equation. What are the coordinate of equation 1? If I am telling here I am writing, if I am putting x2 is equal to 0, so x1 will be 3000 upon 12, and 3000 upon 12 can be written as just like 250. So the coordinate is 250. If I am putting x1 is equal to 0 in this equation, so the x2 is equal to 3000 upon 6, so that become just double 500. So these are the coordinate of this equation. I can plot against x1 and x2. On x1 I will plot this x1, this is x2, so I can easily plot here, right? In next slide I will show the solution. And in second one, you can see the equation again. We can put, if I am taking x2 is equal to 0, so x1 is 2000 upon 4, and 2000 upon 4 become 500, and another coordinate, that is 200. If I am putting x2 is equal to 0, x1 is equal to 0, x2 become 200. In this equation, if I am putting x2 is equal to 0, so that the coordinate become 450, and that one is 300. So this way I can write the coordinate. Once I am able to write the coordinate, I have to convert into the proper scale according to the requirement. Suppose I am taking 50 as a 1 centimeter. 50 unit monetary unit is equal to 1 centimeter. So I have to plot of 5 centimeter line here, and 10 centimeter line here, and this is again 10 centimeter, and this is near 4 centimeter, and this is 9 centimeter, and this is 6 centimeter. So this way I can convert. I have to take a scale and mark 1 2 3 4 5 6 7 8 9 10 just like this, and 1 2 3 just like up to 10, and against this particular point I have to plot a graph, right? So I can easily see the solution. This much of mathematics everyone know, that's why I'm not more focusing on that. So that is the solution, right? So I plot a line 250, this is the lathe machine line. In the last previous one, that is the 250 500, 250 on the x1, 500 on the x2 I have plotted. So lathe line. For milling line, the coordinate is 500 and 200. So 500 and 200. So this is the milling line, and this is grinding line. And all line are representing less than, means the solution always lie in the inner side, below these lines, because all constraint belongs to the less than type. So the solution lie in this side. Right. So the common region, firstly we have to decide the feasible region. Feasible region means the common region. That common region will satisfy all the constraint, right? So the common region of all three lines is represented by the pink color. So this pink color is the feasible region. Means the solution always lie in a feasible region, because this problem belongs to the maximization type. So always the solution maximum value always exists at the corner points. So we have to check the corner points, because this problem belongs to the maximization type. If the problem belongs to the maximization type, means we have to check the top most corner of the feasible region. If the problem belongs to the minimization type, then we have to check minimum corner point of that problem, of that feasible region. So the corner point of this feasible region, corner point number 1, corner point number 2, corner point number 3. There are 3 possible corner points at which the solution can lie, and we have to check the objective function value at these 3 corner points to obtain the optimal value, because the solution will always lie at the corner point of the feasible region, right? So the objective function is very simple here. Objective function is that is 40x1 plus 100x2, that is 40x1 plus 100x2. Now we have to put this corner point, suppose this one corner point, so z1 is equal to, what is the value at this corner point? X1 is equal to 0 and x2 is equal to 200. So 0 plus that is 100 into 200, that become 20,000. Right, another corner point, this is 3, z3, that corner point is 250 0. The coordinate of this point is 250 0. If I put this value, to 400 into 250 plus 0, so that become 10,000. Right, second corner point, now we have to see the second corner point. This corner point is the intersection of 2 lines. Which line? Intersection of 2 lines, intersection of milling line and intersection of lathe line, right? So this corner point lies at the intersection of lathe and milling line. So we have to solve these 2 equations to get the value of these corner points. Means we have lathe equation and we have milling equation. Okay, this is the lathe equation, this equation is the lathe equation, and this is the milling equation. We can solve these 2 equations. This much of mathematics everyone know. We can easily solve these 2 equations. 2 variable equation, easily we can solve it. Right, after solving the solution of this, the x1 x2 lies, and the x1 or x2 value is 187.5 and 125. After solving this 2 equation, lathe and milling equations, by simple algebra we can solve it, and getting the value 187.5 and 125. Right, and at which if we put these value into this equation, we will get z2, and the z2 will be 40x1 187.5 plus 100x2 100 into 125. We will get again 20,000. because this problem belongs to the maximization of these three corner point is the value is 20,000, and we are getting 20,000 at the two different combination of decision variable. One combination is this and another combination is this, and definitely because we have two different combination of decision variables to get the same optimal value of 20,000, that's why I am saying this problem as an alternate solution, or I can say multiple optimal solution. If I am working as a manager of any industry, I have a more than one solution of a problem, then I always feel confident in the organization as a manager, right? So multiple optimal solution always boosts the confidence of manager because it has more than one solution. At the end we have to get the optimal value, at the end we have to get the maximize, we want to maximize the profit as a manager, right? So this way we can demonstrate any multiple optimal solution. Before starting problem, we can identify this problem has multiple optimal solution. Or how we can define a active constraint. Now we can see I plot the slope of the objective function line. If I plot the slope just like just a minute, if I plot the slope of the objective function, here the objective function is z is equal to 0 because it is passing through the origin. Now the direction of the increasing of the objective function line this way, and it will coincide with this line. Now we can see the objective function line is coinciding with the binding constraint. So that's why we are calling, and the solution lies over this line at more than one corner point. So that constraint is also known as active constraint. This constraint is also known as active constraint. Why I am calling it as active constraint? Because the slope of the objective function line increasing, the value of z is 0, z is more than 0, z is here is 20,000. So we are increasing the value of objective function in the direction of binding constraint that is forming the boundary of a feasible region. That's why this binding constraint is also known as active constraint, right? So this way we can obtain a multiple optimal solution problem. Further, unbound solution. The meaning of unboundness means it exists when a LP problem has no limit on the constraint. Means feasible region is not, we are unable to bound the feasible region. If we are unable to bound the feasible region, it means any of the decision variable move to the infinity. If any of the decision variable move to the infinity, then there is a possibility the objective function which has definite or indefinite, which has finite and infinite values, also move to the infinite value. When the objective function move to the infinite value, it means the problem is unbounded. And generally this type of situation arises when the formulation of the problem is not properly done. Means we have always a problem into the description form. In real problem is always into the description form, and we have to convert into the mathematical form. And that transformation is called, from description to mathematical form, is known as transformation. If that transformation is not correct, then generally this unboundness occur. And generally this unboundness is the reason of if any of the constraints have been inadvertently ignored while formulating the LPP. There may be a possibility who is transforming into the mathematical form forget about any of the constraint, any of the restriction, like into the consideration. So such type of problem generally arises due to the when we are not considering all the constraint or resources available to us. So generally the who is converting description form is converting into the mathematical form, and who is converting that description into the mathematical form and not considering all the constraint. So such type of situation arises generally. Suppose a mathematical terms is given, the objective function is given of maximization type, that is 5x1 plus 4x2, and it is subjected to some restrictions. These are two restrictions, and third one is the non-negativity restriction. If I plot this equation on the graph, then I can easily observe and now you can easily plot on the graph. I have give two example how we can plot any equation on the graph. Just we have to write the coordinate of this equation and this equation and plot on the graph and find the feasible region, and then we have to, because the problem of maximization, then we have to see the corner point. At the corner point the maximum solution will exist. So firstly we have to draw this equation, then we will get why this problem is unbound solution. So if I plot the equations, one equation is this, second equation is this, and both equations are, you can see here, and this equation is less than type and this equation is greater than type, right? So if the equation of the greater than type, you can easily observe, means the solution will here, that is the greater than means solution lies here, right? And this equation is here, so solution lies this side. If we are able to find a common region, so that is nearly about a common region, right? So that common region you can see here, in this common region, that is x2 is moving to the infinity, means we are unable to bound this variable, we are unable to bound this variable x2, and it is moving x2 is moving to the infinite. If any of the decision variable is moving to the infinite, it means there is a possibility the objective function is also moving to the infinite. So the problem is unbound. So we can say this problem is unbound. Now further, no feasible solution. No feasible solution means the condition when there is no solution of the LPP, means we are unable to find any feasible region. If we are unable to find any feasible region, so we are unable to find a value that will satisfy all the constraints. It means that the constraints in the problem are conflicting and inconsistent. There is a possibility whatever the restriction imposed that are conflicting and inconsistent. Just like, for example, if I am taking an example, I have an industry, a manager has an industry that the capacity of the industry is producing 500 parts per day. The maximum capacity of the industry is producing 500 parts, any of the parts can produce. And he take a order from outside 800 unit per day. The demand outside is 800, so he is receiving a order of 800, but the capacity of the industry to produce only the 500 units per day. By using hook and crook, only the 500 unit can be produced inside the organization. So we are taking a order of 800 unit per day and we are able to produce 500. What is this? This is conflicting and inconsistent in the constraint. Here the constraints are conflicting. We have the capacity to produce 500, so only we can produce 500, not 800. So we are unable to fulfill the demand. So here the constraints are conflicting, right? So we have to receive an order up to the 500 units so that we are able to fulfill the demand. So this, if the problem is like this, so that problem has no feasible solution. Means we are unable to find a common feasible region that will give the solution of the problem, that will satisfy all the constraints. Just like this, if the problem belongs here, this problem again is the maximization type, right? And the constraint of the problem is given x1 minus x2 is greater than equal to 0. And second constraint is 2.5 x1 minus x2 is less than minus 3. And non-negativity restriction is x1 is greater than 0, x2 is greater than 0, right? If I plot on the graph this equation, if I plot on the graph, so we can find like this: one equation of less than type, another equation of greater than type, right? So here we can see in this equation is greater than type, and this equation again, if I multiply both sides negative sign, so this equation is again greater than type, right? So both equation of the greater than type, so we are unable to find, you can say just like this, we are unable to find any solution. Means this problem does not have any common region. We are unable to find any common region in which the solution exists. That's why this problem is known as no feasible solution. So this way different aspect of this problem can be seen. A LPP may be unique solution or multiple solution, unbound solution or no feasible solution. So there are 4 different aspects In graphical method we can identify by the different way, right? Thank you.